calc one. When you first look at function like this, and they ask you to find the derivative of that madness. Well, ultimately, you need to think of this layer, this composite function, as multi-layered functions. You know, so we have like an outermost function, and then an inner, then an inner, and then an innermost function. And again, nested dolls are here to help us do that. So what are we going to have? So we have the outermost, we have a cosine, and then the inner, that's the exponential, then there's a cosine, and then there's an x cubed. So let's start with finding the derivative of sine. What's the derivative of sine? Cosine of the whole madness here, e to the cosine x cubed. So that's the derivative of the first layer. Let's look at the next layer, which would be the exponential. What's the derivative of the exponential itself, right? Exponential. E to the cosine x cubed. And what would be the next function to differentiate? Cosine. What's the derivative of cosine? Negative sine of x cubed. And lastly, one more. What's the next one? X cubed, right? I don't know what happened. It's upside down. Yes. All right. So that was the last one too.
What's the red one?
The red one, it's one of the guards from Return of the Jedi.
Is there another one?
Yeah, I've been like dying to know. Oh my god!
It's the Emperor, supposedly.
I've never seen that.
I know, but I should have added one more function to see all of them, right? So, and that derivative is just 3x squared using just a general policy, right? All right. So, well, the chain rule in functions of multiple variables, it's going to work in a slightly different way. Because this time, we're going to have a function z that depends on two variables, and at the same time those two variables depend on one variable. Well, for now we're going to look at a case in which we have only one dependent variable that's reflected over here. Those composite functions that are going to be depending on only one single variable, g of t. All right, but of course we can extend this to many more variables, as we will see later. All right, so we're given a function. They're asking us to find dz dt. So notice in this case this is not a partial derivative, it's actually an ordinary derivative. But the function right here, z, contains multiple variables. That's because all these different variables depend on one single variable. So what we're going to do here in this case to get that derivative is to find the partial derivative of the z function with respect to x, and then find the derivative of the x function with respect to t. We're going to do the same with the partial with respect to y of z with respect to y, and then we're going to multiply by that y being differentiated with respect to t. Well, so you'll see this in action in a second, and actually there will be two ways of going about this problem. All right, so number one, okay. So they're asking us to use the chain rule, that is, using this formula, that is the z over dt equals partial z with respect x times dx dt plus dz with respect y, partial z with respect y times dy dt. Well, in this case, we have all the information that we need in the given problem. So all we're going to do is find the partial with respect, the partial of the function z with respect x. Okay, so what's the derivative of this first term with respect x? y squared, because the derivative of x is 1, and the quantity y squared, which is multiplying, is just a multiple constant, so that's y squared, times, well, not times, it's just plus, well, the derivative of the second term with respect x, well, that's 6x. And the derivative of the last term, negative 4y, with respect x, that'll be 0. So let's close parentheses to multiply by the derivative of the function x, which I'm going to highlight with red. Okay. So what's the derivative of x with respect to t? Well, we have only e to the t, which is e to the t, isn't it? And plus, let me go back to the partial of the given function z with respect to y. Well, in this case, what's the derivative of xy squared with respect to y? To xy. All right, and then, and the second term is going to get zeroed out because we're differentiating with respect to y, and the derivative of negative 4y would be negative 4. And now we're going to multiply by the derivative of y with respect t. And what's the derivative of cosine again? Negative sine. All right. Notice we have these variables like all over the place. I agree. Ultimately, we're finding an ordinary derivative, and we're differentiating a function z that depends on t. We already have some terms and factors containing that variable z. All we have to do now that we're done differentiating this, we need to replace x's and y's with whatever corresponds from what we're given. So d z dt will be y quantity squared, which in this case is cosine squared t, plus 6x, which in this case is e to the t, times e to the t, plus 2x, in this case is e to the t, y, that's cosine, minus 4 times negative sine of t. So we're essentially done with differentiating this function. How about let's simplify this a little bit just to make it look nicer without too many parentheses and the signs right here. So this should be e to the t cosine squared t plus 6 e to the 2t, right? Because we have the same base, we're multiplying them, we're supposed to add the t's. And then careful, because positive times the negative from the derivative of cosine, which is negative sine, it's going to turn this into a negative. That's going to be 2 e to the t sine cosine. And then careful, because negative times the negative is positive for sine t. So that's one way. So that's one way to do the derivative using the chain rule. And the other way is by number 1, writing the function z as a function of just t. In this case, we would be substituting these x's and y's where it corresponds on the original function to create only a single value, a single variable function, not a single value, a single variable function. So using the chain rule, what we do is take the partial derivatives and the ordinary derivatives on the original, put it together, and in the end substitute for x and y. This time by first writing z as a function of t is do the substitution first and then differentiate. So let's see how do we go about that. Number 1. So let's write z, not yet the derivative. So in this case, xy squared, where x is e to the t, times y squared, which is cosine squared t, plus 3x, which is e to the t, and actually squared, so that's going to be e to the 2t, and minus 4y, which is cosine. So notice in this case, our function z does not have more than one variable. It only has one single variable. So basically, this is a calc 1 type of problem that we're going to do. Take the derivative. That's why, check this out. That's why the notation for our derivative, it's an ordinary derivative and not a partial derivative. So let's take the derivative. dz with respect t. So in this case, we're gonna need the product rule over here, right? So the derivative of e to the t times cosine squared. Well, actually, how about, let me write down the product rule. Whenever we have uv prime, that's u prime v plus v prime u. That's our product rule. Let's apply that product rule to the first term in this given function. So the derivative of e to the t, which is itself e to the t, times cosine squared t. That is the v without doing anything at all. Now, to differentiate cosine squared, what do we do to differentiate cosine squared? We can split it, or how about write it as a cosine t quantity squared, and that's like a mini chain rule, right? So that's a 2 cosine t times the derivative of cosine, which is negative sine. Well, that's only the v prime. We still need to multiply by u, which in this case is e to the t. All right, let me label this, because we're going to have a bunch of terms just so you can see which one is which. So this is u prime v plus v prime u. Right? That's the product rule in action for that first term. To differentiate the second term, so all we have to do is multiply 3 times 2. That's going to give us a 6 e to the 2t, because the derivative of e to the t is e to the 2t is itself times the 2, which is the derivative of the exponent, but that's 2 times this 3 right here becomes a 6. And finally, the derivative of cosine, which is negative sine, that's supposed to be for sine. All right. And well, is there anything interesting to do about this one? I don't think there's anything else. Actually, there's nothing to simplify other than cleaning up the parentheses. E to the t cosine squared t plus, or actually negative 2 let me do 2 sine t cosine t e to the t plus 6 e to the 2t plus 4 sine t. And these two answers actually match. Maybe the order of the terms I wrote it, but I mean it's essentially the same. Now, the question is, which one is better? Which one is easier? Well, I mean, it looks like both methods require some writing, both methods require some work, so I don't think it really makes a difference to do it one way or another way, right? So I would say in this case, well, it depends on what you would be asked to do. Actually, my MATLAB might ask you a part A again, like doing the chain rule, set it up, type the first derivatives first, and then in the end just come up with the end result. All right, so let's see. Example number 2, and this is some sort of related rates as well from calculus 1, and again we have a problem with an ideal gas. The pressure, volume, and temperature of a mole of an ideal gas related by the equation PV equals 8.31 T, where P is measured this time in kilopascals. Well, that's kind of weird because usually it's atmospheres, right, when you use the ideal gas. Well, V is in liters, that's fine, and T is in kelvins. So they're asking us to find the rate at which the pressure is changing when the temperature is 300 Kelvin, increasing at a rate of 0.1 Kelvin per second. Also, the volume is 100 liters and also increasing at a rate of 0.2 liters. So you might remember this kind of problems from back in Calc 1. So depending on what they're telling them how the variables are changing, if they are increasing or decreasing, well, that has to do with the sign that we're going to use in the end when setting up, when doing the calculation. So, number one, let's write down what are they asking us for and what do we have. So, in this case, they're asking us for the change of the pressure with respect time. So that's what related rates were about. So in this case, two quantities changing with respect time. I mean, like the easiest case when you inflate a balloon. So there's a couple of things changing. So in this case, the volume is changing, increasing or decreasing due to the radius of the balloon, that it's also changing, whether increasing or decreasing. Well, of course, assuming the balloon is perfectly spheric, which is, well, not always the case, but that's the typical example that we do. But in this case, we have more than one property changing, and those two change over time. In this case, everything is also changing over time. So that's the question. And then temperature is 300 Kelvin, and the temperature is changing with respect time at a rate of 0.1 Kelvin per second. Also, we have a volume of 100 liters with the volume changing with respect time at 0.2 liters per second. Let's not care about the units for now, because otherwise we're gonna have like a lot of symbols. We can just make sense of the units in the end. So this equation that we have here, this function PV equals 8.31 T. How about in this case we solve for the variable P, for the pressure, because we want to find the change in the pressure with respect time this time. So let me write it over here. So that's going to be P equals to 8.31 TV to the negative 1. Because essentially we divide both sides by V, and then we have the V to the numerator with negative exponent. Well, so what are we going to do? In this case, we're going to use the chain rule with one independent variable, but in this case two dependent variables changing at the same time. In this case, temperature and volume. So that's the change dP dt. That's going to be the partial derivative of the pressure with respect time, or actually with respect to temperature here. Oh, hold on. What do I have? Should be the temperature, yes. And times the rate of change of the temperature with respect to time, plus the change on the pressure with respect to the volume, because in this case, in this system, the pressure is changing, is being affected by both changes, a change in the temperature at the same time as a change in the volume as well. All right? And both are changing with respect time. All right? So what do we need to do? So number one, let's find the partial derivative dP dt on the given function. So okay, so in this case we have P equals 8.31 T V to the negative 1. So we want to differentiate the temperature. So what's the derivative of just T? Isn't that just 1 times every multiple constant, which would be 8.31 V to the negative 1. That times dt, the change in the temperature with respect to time. But the good thing is not an expression, it's just a numerical value, in this case 0.1, plus the partial of the pressure with respect to volume. So in this case, that's going to be negative 1 or negative 8.31 t v to the negative 2 times dv dt. In this case is 0.2. Well, so we're almost there. So how about we first write these negative powers as positive powers and change these signs right here. So this will be 8.31 over v times 0.1 plus, or rather minus 8.31 t 8.31 t over v squared times 0.2. And well, all we have to do from here is evaluate the derivative dp dt at the point where t, the temperature is 300, and the volume is 100. So we're going to plug in 300 wherever we see the letter T, which is just going to be here, and 100 for letter B. So that's 8.31 over V, which is 100, times 0.1 minus 8.31 T, which is in this case 300, divided by 100 quantity squared. And after doing all these calculations, well, this would be approximately, well, I got a negative 0.04155. And in this case, what do we have? Well, so we're finding the rate of change between the pressure and time. So that means, in this case, kilopascals per second. Right. Kilopascals per second. And well,
0.2 at the end of the...
which one?
Your 0.2.
Oh yeah, the 0.2. I forgot that one. Thank you. All right. And yes, that's a related rate type of problem, but in this case involving more than one property in this case, right? What's next? Oh, chain rule, but having in this case two independent variables. All right, these ones are gonna be fun. All right. Well, in the previous case, what did we get in the previous case? So of course the same function z, and in this case it's a function f of x and y, but at the same time those x's are g and h respectively, but this time not anymore depending on just t like in the previous case. This time these independent variables are 2 this time. So that means that we are going to find two expressions. In this case, we're going to find two derivatives, one with respect s and another one with respect t. All right, so in this case, let's call this s and t to be the independent variables, because those are the very last ones, derivative that we mentioned, and this x and y are the intermediate variables, and z is of course the given function that's going to be our what's it called, the dependent variable. So z is the dependent variable. Well, to have a better visual of what we're going to do here, so I think a tree diagram is going to help us here. So, for example, we're going to start with this, a function z. This function z depends on two intermediate variables. In this case, those two intermediate variables are, for now, x and y, which at the same time those x and y depend further on s and t. All right, so how are those two expressions obtained in here? So in this case, we want to obtain all the possible ways that can take us from z all the way to s. So for example, if we start at z, if we go this way, well, let me use pen instead. So to get the partial derivatives with respect s, we have to go first through x, and then from here go through the variable s. That is, so the partial of z with respect s, that's equal to first the partial derivative of z with respect x times the partial derivative of x with respect s. But that's not the only way to go from z to s. There is another way. There's another pathway, right? So the other one is to go to y, and then from y to s, plus partial z with respect y times the partial of y with respect s. Alright, so that's how we got that first expression right here. This one. Now, to get the other expression, that is the partial derivative of the function z with respect t, what are we going to do here? Well, so instead, we're going to go z with respect x and then x with respect t. So that is partial z with respect t. So that's the partial of z with respect x. And then we're going to differentiate the x with respect t. Plus, there's another way, there's another pathway in our tree diagram that would take us from z all the way to t. That's going to be like doing z from z to y and then from y to t. That's the partial of z with respect y, and then times the partial of y with respect t. Alright? Can we have more functions? Like more independent variables, more intermediate variables? Of course. What if we had something like this? A function w that depends on x, y, and z, and then at the same time this x, y, and z, they all depend on s, t, and u. S, t, and u. S, t, and u. Alright? Now, well, I'm going to do only one for this. So, suppose we want to find, let's say, the partial derivative. So, in this case, there's three changes. So, this function w would be changing with respect three independent variables. Would be changing with respect s, with respect t, and with respect u. So, for example, the one for dw with respect s, dw with respect with respect t, and dw with respect u. I'm going to do the second one. And the other ones, well, I guess you're going to get the idea in this case. So, first of all, let's look at the tree diagram and see how many ways do we have to go from w all the way to, in this case, the one that we're interested in this case is t. So number one, we can go from w to x, and then from x to t, and then from w to y, and then from y to t, and finally from w to z, and then from z to t. Let's write those partial derivatives. So partial w with respect x times partial x with respect t, plus the second possibility in all our paths here. So that's the partial w with respect to y, and then the partial with respect to y, the partial of y with respect to t. And last but not least, the partial of w with respect z times partial z with respect t. All right. Well, ultimately, check this out. I know these expressions look crazy. However, if you notice here, the partial x cancels, partial y's cancel, leaving us with partial z with respect to t, partial c with respect to t. But all these factors that we keep adding and adding, that's due to the intermediate variables this w goes into in order to get all the way to the independent variables. All right. So let's do an example using this partial derivatives, and in this case for two variables. All right. Number one, let's see, we are given the function z equals e to the x sine y, where x is a function, not just a function of t like in the previous problem, is now a function of two very independent variables, s and t. So x equals st squared and y equals s cubed t. All right, so what do we need in this case? So they're asking us to find the partial of z with respect to s. And I know we have like a one function of two intermediate variables and two independent variables. If it works for you, I would do it. Why not? Do a tree diagram. So z depends on x and y, all right? But also at the same time, x depends on s and t, just like y depends on s and t. Are you guys following me up to this point? All right, let's find the partials. Well, so they want us to find the partial derivative of the function z with respect to s. Well, that means we need to go in this direction from z to x and then x to s. In other words, we want to evaluate partial z with respect x and then the partial of x with respect z. I'm going to compare this with the previous example just so you can see how the notation in that's s, right?
Yeah.
Yes. Yeah, I kind of read your mind. I knew you were going to say that, right? Yeah. So the other way is z with respect to y and then from y to s. Okay? dz over dy, dy ds. Alright, so that's going to give us all the changes in this case. Alright, so we have everything we need to find these partial derivatives. Okay, so the partial of the function z with respect to x, and notice we have z depending on x and y, so that should be a given. Okay, so with respect to x, well, what's the derivative of e to the x? Just e to the x, but this sine y, it's a multiple constant, so it's going to be actually itself e to the x sine y times the partial of x with respect to s. In this case, notice this x depends on s and t, so it makes this second factor should make sense. Well, so what's the derivative of s t squared with respect to s? T squared, right? Because the derivative of s is 1 and the t squared is a multiple constant. Well, in this case, that's just going to be t squared. What if we had x equals s plus t squared instead? What would be the derivative of s plus t squared with respect to x? Just 1, right? Just 1. So this is, in this case, t squared. Okay? Plus the partial of z with respect to y. Well, in this case, what's the derivative of sine? Cosine cosine times the multiple constant e to the x times the partial of y with respect s. Well, what do we have for s? Q plus t. That'll be 3s squared. Oh, yes, 3s squared t. All right. So that's our partial derivative. That's about it. So the next thing we want to do, now that we're done with finding the derivatives, how about replace x's and y's where it corresponds? So in this case, x is the same as st squared. It's going to go here and here. And y, which is s cubed t, it's going to be here, that's going to go here and here. So let's go about it. So this will be then, so partial z with respect s, that's e to the x, which is st squared, and sine of y, which is s cubed t, times t squared plus e to the x, which is st squared, cosine of y, which is s cubed t, times 3s squared t. And while there's really not that much to simplify, all I would do is just clear these parentheses right here, put this st in front of the exponential. There's really not that much. So that's what's it gonna be? Did I miss something? I think. No, I think we're good. No, we're good. I was looking at the wrong one. So that's t squared e to the s t squared sine s cubed t plus e to the, oh, not e, actually 3s squared t e to the s t squared cosine s cubed t. So that's the partial of z with respect x. Now let's compare with the previous example, so we can compare both the notation and the setting of the problem, so you can see the differences here between one independent variable versus in this second case, which is two or more than one independent variable. And you can see that from the notation. So for example, in the previous case we got something like again, we had only one independent variable, so that's why there's no need to use partial derivatives. So for this reason, in the notation here we had ordinary derivatives because it's only one variable, t, as opposed to the next case in which x and y now depend on more than one variable, s and also t. So that's why these ones right here are now partial derivatives. So no need for partial derivatives for the previous case, but now we have that need. All right. Okay, so now we want the partial derivative of the function z with respect t this time. So number one, how about we set up like a roadmap here, if you will. So number one, z changes with respect x and then with respect t. So that's partial z with respect x and then partial x with respect t. And on the other hand, z changes with respect to y before changing with respect t. So partial z with respect y times partial y with respect t. So with our expressions here, it looks like we got number one, partial of z with respect x. Again, it's the same, e to the x sine y times the partial of x with respect to t this time, which in this case is 2st. Is that what you got for this one? Plus partial of z with respect to y, that's e to the x cosine y, times the partial of y with respect to t. And well, the derivative of t in this case is just 1 times s cubed. It's just s cubed. Alright? And well, the rest is just back substituting again with the same color coding here. Okay, x is st squared, and y equals s cubed t. So this will be, so that's e to the x, which is st squared sine of s cubed t times still t squared, plus e to the st squared cosine s cubed t times s cubed. And really, again, there's not much to simplify. Maybe factor out the exponential. No need. That's fine. All I'm going to do is clean up the parentheses. So that's going to inhabit the polynomials in the front. T squared e to the st squared sine of s cubed t plus e to the st squared, or rather s cubed in the front, cosine s cubed t. Yes?
Where did the t squared come from?
The t squared coming from
Second line.
this one?
That one.
This t squared, that's the derivative of x with respect to t. Oh, no, that's 2st. Yeah. 2st.
Are they not supposed to be the same? The two A and B?
2a and b. No, not in this case. No, that would have been if we were doing the mixed partials.
Are you
Yeah.
allowed to do it backwards where you like do dz dy times?
It's fine. So notice in this case I didn't ask you to do the chain rule. Well, actually I did the chain rule, but you could have done it the other way. Substitute everything first and then just take the two partials, one with respect to s and one with respect to t. Either way, I mean, I guess it would take about the same amount of work. So let's see what's next. Okay.